Okay, so this is notes on polar systems. The first thing I'm going to do is show you what a polar system is. It's just two equations, polar equations, that we're going to find the solutions to. Normally we just look for intersections, but and for polar, because order matters, you have to find the simultaneous intersections. Okay, so what we're going to do first is do this in our calculator. This won't really be beneficial for every problem, but for this first one, it's a nice little introduction. Okay, so go ahead and get your calculator out. Make sure you're in polar mode, radian mode, polar mode. And I want you to notice another thing I did. I changed this to simultaneous. What this is going to do is graph the two polar equations at the same time instead of the first one and then the second one. Okay, then you're going to go to y equals. I already have mine typed in. And one last thing I'm going to do, you might have seen this before. You know, if you press enter once, it's bold. If you press enter one more time, what it'll do is it'll kind of put a little head at the beginning of your graph. So if you're really caring about the motion of the graph, this is a nice thing to see. All right, and a good zoom for this, we want to kind of be in tight, is a zoom 4. So I'm going to press zoom 4, and what I want you to look for is simultaneous intersections. Where's the graph intersecting at the same time? Okay, so here we have something, and we have an intersection there once, and then it looks like they're getting closer, and then there's another intersection right there. And if you were just to look at the end product, it would look like I have another intersection at the pole and one more here. Okay, but we're only interested in simultaneous intersections. These two are fairly easy to pick out because they're on what looks like the y-axis, but this is really pi over 2 and 3 pi over 2 with a radius of 1. And so you can actually, on some problems, find them, but on others it's a little bit harder to do. So we're going to have another way to actually find them that works for everything. So I want you to draw this picture in. You know, it kind of looks weird like a spider, but here were our two simultaneous intersections. Note that I did not put the pole and this other point out here because they weren't simultaneous. Okay, now let's solve this out algebraically. This will be the bulk of today's lesson. Okay, so what we're going to do is we're going to solve a system just like any other system. We're going to use substitution. So I'm going to let 1 equal 1 minus 2 cosine theta. Notice that there's a qualifier over here. It's usually this, the first revolution. Okay, now I'm going to subtract 1. That's going to give me 0 equaling to negative 2 cosine theta. And then I'm going to divide by negative 2. So I have 0 equaling to cosine of theta, or I could really rewrite this as theta is equal to arc cosine of 0. And now we're going to talk general solutions. All right, theta is going to be equal to, what would be the principal value of arc cosine of 0? It'd be pi over 2, 90 degrees. And then remember that we can also include all the values where you add or subtract 2 pi. Now, that's really not going to be that big of a deal in this one because it will put us outside the revolution. But let's say this had been 2 theta and I had to divide by 2, then it might make the difference. Also with general solutions, remember that we did have 2. Now, you may or may not remember the rule. If you don't remember the rule, just think, where else is cosine 0? At pi over 2? And then using quadrantal angles, or maybe the OIO chart, also 3 pi over 2. And we're also going to put a little plus 2 pi in. Now, in the end, we didn't have to do that because I really only have 2 angles in the first revolution that work. Alright, so now I have my angles, and what I need to do next is to find the radius. Now, this one actually kind of makes this easy for you because the radius is always 1. So one of my answers is going to be 1 pi over 2, and the other answer is going to be 3 pi over 2. We'll see what to do next if the radius is not always a number. Alright, and one more thing we're going to go ahead and start looking for is by checking the pole. The pole may be a solution, and you may miss it by solving it algebraically. This is something you always have to check at the end. Okay, to check the pole, what you're going to do is you're going to let r equal 0, and you are going to see if it's even possible to solve for theta. So in the first one, if I let r be 0, I have 1 minus 2 cosine of theta. And if you were to solve for cosine of theta, you would have 1/2. Now we know that cosine of theta does sometimes equal 1/2, so that one's okay. Now we obviously are going to have a problem here when we let 0 just equal 1. This is an obviously false statement, so the pole is not a solution. But if both of these could be solved, it doesn't even matter what theta is. If it could be solved, then 0, 0, the pole would be a solution. Okay, let's do another example. We're going to start this problem off the same way we did the other one. We're going to let the two r equations be equal to each other. So sine of theta is equaling to 1 minus sine of theta. And as you solve this, okay, you're just going to use all those good algebra rules. Remember that the whole point here is to find theta. So if you added sine over, you have 2 sine theta equaling to 1. So sine of theta is going to equal to 1/2. We're in good shape. We know how to do this. Theta is equaling to arc sine of 1/2. And when you're thinking about general solutions, this is going to give you a 30-degree angle, or pi over 6, plus 2 pi n. All right, and theta, where else is this? You may or may not remember the rule. Just think, where else is sine a positive 1/2? In the second quadrant. So what you need to do is put pi over 6 in the second quadrant, 5 pi over 6. And if you remember the rule, it was pi minus the principal value for sine. If you don't really remember those rules, don't cling on to them now, because they failed you after only a couple months. So just think, where else is sine positive 1/2? In quadrant 2, 5 pi over 6. All right, and again, I'm writing this out very formally, but really you could come to this conclusion without doing all of this work, but you're going to have to think through it and make sure you're not missing anything. All right, so let's go through, and I'm going to kind of draw a line here, and let's find the r for pi over 6. Okay, so what we're going to do is we could actually plug in pi over 6 into either one of these or both. So what I would do is just pick the easier one. But if you feel like you're prone to mistakes, plug it into both and make sure that it matches up. So if I plug it into the top one, which is the easiest thing to do, I have sine of pi over 6. That's going to give me 1/2, which makes sense because we just came from there. So then one of my solutions is going to be 1/2 comma pi over 6. All right, that is a solution. All right, now for the other one, same thing. And again, I'm plugging it into the first one because that's easier to do. You really could plug it into either one, and hopefully you can kind of pick up on the fact that if I were to plug it into the next one, on this one, 1 minus 1/2 is 1/2. Okay, so this also gives me positive 1/2. Make sure you're not leaving off negatives. All that kind of stuff is going to throw your answer off, and it's extremely frustrating, I know, so you have to be careful. Okay, those are my two answers. What I need to do now is to check for the pole. Remember, to check for the pole, you let r equal 0. So if I let r equal 0 in the first one, I have 0 equaling to sine 0, and yeah, this is something I could solve. Sine of angles, some of the time, it is 0. We got that. I can take arc sine of 0. All right, let's look at the next one. 1 minus sine of theta equaling 0. This would give me a 1 equals arc sine of theta. And yeah, I can take arc sine of 1. Okay, so in this case, yes, the pole 0, 0 is a solution, and that would be a simultaneous intersection if we looked at it in the graph. So here I have 3 solutions. Okay, let's do one more. Okay, we're going to start it off the same way we've started off the others. This one works out just a little bit differently. It's in the first couple steps, and that is I can't combine the cosine or sine, so what I need to think is maybe I need to divide and make this into a tangent. So if I divide by cosine, and I have sine of theta over cosine of theta, I can make that into a tangent. All right, so I did that. I'm going to divide over the 2 while I'm at it. I'm not doing anything fancy here. I'm just moving the things around, dividing them around. So on the left-hand side, I have root 3, and on the right-hand side, I have tangent. So this means that my theta is equaling to arctan of root 3, and I can take that. I can figure that out. Okay, that's going to give me pi over 3, 60 degrees. And then remember, if we do general solution, we need to do plus pi n. Okay, so here, pi over 3 is an answer, but also I need to add pi to it. Okay, and that's going to give me 4 pi over 3. Now let's say you were just blanking on general solutions this day. It would be okay because, again, if you're thinking about, all students take calculus, pi over 3 is in the first quadrant. Where else is tangent positive root 3? In the third quadrant for 4 pi over 3. So either way, you're going to get these thetas. Okay, so for the first one, for this one, let's go ahead and find r. Pick the easiest one to do. I'm going to pick the second one. R equals 2 sine of pi over 3. Remember, pi over 3 is a 60-degree reference angle, so this would be 2 times root 3 over 2, or root 3. So one of my solutions is root 3 comma pi over 3. And again, you would get root 3 even if you plugged in pi over 3 into the top equation. Okay, so there's one solution. All right, let's find the other one for 4 pi over 3. And again, I'm going to plug it into the second one because that's easier. So 2 sine 4 pi over 3. So I have 2 times, this actually gives me a negative root 3 over 2. All right, which gives me a negative root 3. So this solution is negative root 3 comma 4 pi over 3. All right, now I just want to think about this for a minute. We didn't even check this on the last one, but it's possible that these two are the same points. Remember, polar coordinates, there are infinitely many ways to write a single point. Okay, so I'm going to draw a little grid down here. And root 3 pi over 3 would be about right there. Okay, 4 pi over 3 would be complete opposite. It's a difference of pi, and it has a negative radius. So actually, these two things are the same point. You can list both points. It's not wrong, but you really don't need to list the second point. It's just a repeat of the first one. And that happens sometimes. We even saw that in trig. All right, now let's check the pole. Remember, when we check the pole, we're going to let r equal 0, and we're going to see, is it even possible to solve for theta? So I let 0 equal to 2 root 3 cosine theta. And we know that if this is, what I'm really trying to solve here is cosine theta ever equal to 0? And the answer to that is yes. And 0 equaling to 2 sine theta, same thing, yes. So the pole is a solution. 0, 0 is a solution, and you have to check for it. You don't want to leave it out if it's a solution. All right, so bring your questions to class. We'll practice this tomorrow.